So before watching this lecture, make sure you have a good understanding of the linear regression model when we have one explanatory variable. In this lecture, we'll extend this to cases where we have more than one. So we're going to have several explanatory variables. So we will still have one dependent variable or explained variable. No change to the setup here. So to consider a simple example, let's say I have this data where this is my dependent variable, the final result on an exam. I now have three explanatory variables, the result on the SAT score, the verbal section, SAT score, the math section, and the high school GPA. So we'll do something that will seem a little bit weird at the beginning, and that is we will actually call the first explanatory variable, we will call that x2 and not x1. It will become clear later on why we do that. So here's part of my data. This is the one that we want to explain. This is my y variable. That's pretty clear in this example. The final exam happens after the result on the SAT and the GPA from high school. We have three explanatory variables and we are going to denote this by x2. This is the x2 variable. This is the first observation, the second one, and so on. So this number here, we'll call that, just like before, y1, the first observation on the y variable. So it's simply the final result for student 1. If we go down and just generically say that this is observation I, where I is any value between 1 and n, then we'll denote this one by yi. So that just corresponds to an arbitrary student I. We have to do something with the notation for the x variable since we have several of them, and what we do is the following. So xi2, we have two subscript now on the x variable, will denote the ith observation for this first explanatory variable. Note how we always put the student number first and the 2 after that, referencing to the first explanatory variable. So that means that this number here will be denoted by x12. It's the first observation for variable x2. And for a generic student I, we denote this by xi, comma 2. Sometimes we just skip the comma if it's not confusing. Like here, it would be confusing to skip the comma because then it would say x12. But between I and 2, it's not confusing, so we might just as well write I2. Moving on then to the next variable, that's going to be called x3. So this will be x3 and this will be x4. Same type of convention here. This will be denoted by x1, 3. This refers to the observation, and this will tell us which x variable it is, where 3 is equal to SATM and 2 is equal to SATV. And this is x1, 4. This would be xi, 4. And sometimes we simply just say xi, j to refer to an arbitrary number among the explanatory data. So I would be some number between 1 and n, referring to which student it is, and j would be any number between 2 and 4, referring to exactly which of the x variables we're thinking about. But we'll now try to create a model which allows all three of them to influence the final result. In this particular example, we had three explanatory variables denoted by x2, x3, and x4. The number here, that is the index of the last explanatory variable, will always be denoted by k. So for this particular setup, k is equal to 4. K will always be 1 unit above the number of explanatory variables, and that's because we begin at 2 and not 1. I should warn you that perhaps half of the literature would use the symbol k to represent the number of explanatory variables. So they would use k equal to 3 for my data set. And the other half uses this notation that k is 1 plus the number of explanatory variables. You'll see in a second why we start with x2 and why we let k be equal to the number of explanatory variables plus 1. But this is the convention that I will use in all my lectures. It's better in the sense that when you continue to do econometrics using matrix algebra, then this is the definition you would use for k. So xk is the final explanatory variable, and in total we have one less explanatory variable, so we have k minus 1 of them. So with this setup, we are ready to define the linear regression model. So I now have a random sample and I have several explanatory variables. So you still need to think of this as being a random sample where this entire row is a sample point. So that's one sample point, all the data corresponding to one student. The assumption then for a random sample is that this data that you see in one row is completely independent of the data that you see in another row, because that represents another student. So there is no correlation between any of these random variables in row 1 and any of the random variables in the sixth row. However, in the same row, there is of course correlation between the different variables. A student, for example, with a high GPA, well, we would expect that student typically to get a better result on the final, even though for these two students, no, it's true for these two students. The first one, higher GPA and higher final score. But we would certainly not rule out dependence between these numbers. Right, so random sample, one dependent variable and several explanatory variable. Then we formulate the linear regression model as follows, and it looks a little bit nasty to begin with, but it's actually not so bad once you get used to it. Let's try to break this apart a little bit. So remember the LRM with one explanatory variable, we wrote it like this: yi depends on a linear function of xi, the deterministic part, beta 1 plus beta 2 xi. That's the deterministic part, and there is also a random part, epsilon I. Now let's just slowly build this up to two explanatory variables and see what happens. So now yi is, well, we still have an intercept, beta 1. We have a beta 2, which measures the effect of the explanatory variable. Now, remember, we have to rename the explanatory variable. We have several of them, so we have to rename them. And remember that we rename the first one to I, 2. We start at 2 and not 1. Now I have a second explanatory variable. So let's just add that to the deterministic part in exactly the same way. That will have its own parameter, beta 3. And we have xi comma 3, like this. So this is my new deterministic part. The deterministic part is now just a linear function of two explanatory variables, x2 and x3. It's still a linear function, as you can see, and we allow the effect that x2 has on y to be different from the effect that x3 has on y. And finally, we have to add an error term, and there's no change in that one. So going from 2 to 3 explanatory variables is just now a matter of tacking in here, just adding beta 4 xi comma 4. That's what we would do. We just tack that in between beta 3 xi comma 3 and epsilon I. And then we can just keep on doing that for as many explanatory variables as we have. And if I want to write this in a generic way, that is without specifying exactly that I have 3 explanatory variables, we need to do it like this. So yi is my intercept. Here comes my first explanatory variable with its parameter beta 2. Here comes the second with its parameter beta 3. Then we need to do this plus dot dot dot, because in between here comes, well, you can figure it out, beta 4 xi 4 and so on, all the way up to the final explanatory variable, which we denote by xi comma k, and that has a parameter of beta k. So this whole part here is the deterministic part, and then we tack on the error term to make it possible for yi to also depend on other stuff that we don't measure. So from this you can actually see the reason for why we do not name the first explanatory variable I comma 1. And the reason is the intercept. That's sort of the culprit here. That one, I want to call that beta 1. Well, if I had named the first explanatory variable xi comma 1, then there would be a mismatch between these two numbers. It was a beta 2 xi comma 1. So we prefer to start with 2 such that the 2 here in front of the beta always matches the 2 here for the x variable. And that's always going to be the case. So if you see a beta k here, you're going to say an xik here. That will be the case in the linear regression model. This thing of having the same index for the beta and for the x is important. So authors that prefer to call the first x variable xi1, they would instead do beta 0 for the intercept. So they would do beta 0 plus beta 1 xi1 and so on. And that's just equally common to this notation. So just pay attention to that when you look at other literature, because there is this these two equally common conventions for the linear regression model. So now we can just go back and do everything that we have done for the linear regression model all over again, but now with several explanatory variables. Fortunately, it's not so difficult, so we can actually do this fairly quickly because it's so similar. The first thing we can say is that we can view this as a data generating process, just like before. We think of the x variables as being simulated somehow. They are random variables. And we think of the y, the dependent variable, as being simulated from a model like this. Just like for the regression model with one explanatory variable, if I make no additional assumptions, then we really have no hope in trying to figure out these beta parameters. So I need some additional assumption for for it to be even meaningful to continue the analysis. And the assumption is actually the same as before. In the one variable case, the thing that we really needed was the exogeneity assumption. So let's talk about that by taking conditional expectations. So if we look at the conditional expectation of yi, we just take the conditional expectation on both sides. Where, and this needs to be pointed out, I am now conditioning on xi. What that means is that I'm conditioning on all the explanatory variables for that individual. So take a data set like this. I am now asking, what's the expected result that a student will get on the final, given that this student had a particular SATV score, a particular SATM score, and a particular GPA score. That is, I want to figure out the expected result on the final score once these are given and known. And it's pretty clear that these values ought to affect this expected value. If you see very high values for these three, you would expect to see a higher value for the final, and vice versa. So we're treating all the explanatory variables as known, and that means that I can simply remove the expectations operator on this first deterministic part because it's known when I condition on xi. And then I have this final conditional expectation of the error term given all the x data. When you read this, I think it's a good idea to have the notes for the linear regression model with one variable next to you so you can see the differences, and in particularly see that the differences are very, very minor. So as we pointed out, this expected value yi conditional xi is just shorthand notation for reconditioning on all of the explanatory variables. It's just messy to write out all the explanatory variables, so it's nicer to write it like this. So on to exogeneity. So we're simply going to say that the x variables are exogenous, quickly fixing the grammar, if this is true. So if the expected value of the error term given all the explanatory variables is 0, that is, the error term must have a 0 expectation no matter what the value of the explanatory variables are. The first student has these explanatory variables. In the model, we need to add an error term for that student. That error term must have an expected value of 0. The second one has a different set of explanatory variables, but the expected value for this student of the error term must also be 0, and so on. All of them. No matter what the values of the x variables are, the expected value of the error term should be 0. So we're really trying to avoid here is having error terms that are in some way correlated with one or more of these explanatory variables. If this happens, that last term in the conditional expectation will go away and we have this result. The conditional expectation of y given x is this linear function conditionally on x, treating x as constant is just a regular linear function of k-1 variables. So that means that we can combine the whole thing together and write it like this. And this notation is pretty nice because in this notation, the linear regression model with one explanatory variable looks exactly the same as the linear regression model with several explanatory variables. And that's just simply because the linear deterministic part is collected in this expected value. Moving the conditional expectation to the other side, we also have a formula for the error term when the x variables are exogenous, and that's this one. So with exogenous explanatory variables, the error term is just again the difference between what we observe, yi, and what we expect to observe according to our model. So some students will experience a positive error term and get a better result on the final than we would expect from the explanatory data. And some students would experience a negative error term. We can also do this for an arbitrary student, a student which is not necessarily in the sample. So just an arbitrary observation. And what we do is we simply just remove the I subscript and keep everything else, because we're not now pointing to a particular student. We're claiming that the relationship hold in general, and then we can write it like this. So the expected result on the final given specific values for SAT scores and GPA is this linear function of the scores and GPA. Again, in this case, conditionally on X is shorthand notation simply for conditioning on all the explanatory variables. This makes it easier to write. This specific notation allows us to really formally interpret what these beta parameters actually are. And they are derivatives of this left-hand side expression. Well, except the intercept, of course. So the intercept beta 1, we can view that as the expected value of y when all the x variables are 0. For our particular example, it doesn't make any sense because that would be the expected score on the final for a student that had 0 GPA and 0 on all the SAT sections. We probably don't have any student in the sample which is even close to that, so in this case that doesn't make too much sense. But that's what it is. It's the expected value of y when all the explanatory variables are 0. So this x equal to 0 without the specific subscript, we have to interpret that as all of them are 0. Well, how about beta 2 then? If you just differentiate the expected value with respect to x2, you're left with beta 2. So clearly, beta 2 is the derivative of this conditional expectation with respect to x2. But that's true for x3, x4, all the way to xk as well. So generally, beta j for any j between 2 and k is the partial derivative of the conditional expectation with respect to the x variable. How should we interpret it? Well, let's, for example, think about beta 2. Beta 2 is connected to x2, that is to SATV. So the interpretation of beta 2 is as follows. If you increase SATV by 1 unit, what would you expect the final result to increase by? That's beta 2. Beta 3, if you increase SAT-M by 1 unit, what would you expect the final exam to increase by? And beta 3 is related to the GPA in precisely the same way. So the main points for the LRM in the case with several explanatory variables are pretty much the same as the case with one explanatory variable. We observe data on now several x variables and one dependent y variable. We make the LRM assumption, and it is an assumption that sometimes needs to be challenged. We'll talk about that more later on. But we do assume that the expected value of y given the x data is a linear function of this particular x data. That's built into the LRM. And the final step is then for us to make estimates of these betas, because the actual true values of beta have typically important meaning to us. We often really want to know these values for a lot of applied cases. And as we will see, As long as the explanatory variables are exogenous, we have a fighting chance of actually estimating these betas, and we'll discuss that in the next lecture, precisely how we estimate these betas when we have many explanatory variables.